going to discuss about magnetically coupled circuits. And the objective is to understand the basic concept of self-inductance and mutual inductance, to understand the concept of coupling quotient and dot convention in circuit diagram. Coming to self and mutual inductance. Okay, self-inductance and mutual inductance. Here, when two loops with are without contacts between them affect each other to the magnetic field generated by one of them, then they are said to be magnetically coupled. Okay, when two coils are, having no contact between them, affect each other to the magnetic field. The magnetic field generated by one of them, then they are said to be magnetically coupled. Okay. Example: transformer. Okay. Actually, transformer is an electrical device which transfers the electrical energy from one circuit to the other circuit without changing sequence. Okay, it is an electrical device designed on the basis of the concept of magnetic coupling. Okay. This transformer uses magnetic coupling, okay, to transfer energy from one circuit to other circuit. Okay, it is a device. It is an electrical device which transfers electrical energy from one circuit to other circuit without changing sequence. Okay. Here, see, I will come back to this magnetic coupling. Okay, here, this is called magnetic coupling. Okay, here we have two coils. Okay, two coils. Magnetically, they are coupled each other. Okay, there is no physical connection between these two coils. There is no physical connection between these two coils. Okay, they are coupled magnetically. Okay, there is no physical connection between these two coils. Okay, these two are coupled magnetically. Okay, there is magnetic connection between these two coils. Okay, these two coils are said to be magnetically coupled. Okay, these two coils are separated physically but coupled magnetically. Okay. Coming to self-inductance. Let time varying current source is given to this coil. Okay, when current I flows through a coil, a magnetic flux phi is produced. Okay, this is time varying current, alternating current. This is alternating current. Okay, so when alternating current is given to this coil, then magnetic field will be produced in this coil. Okay, let phi is the flux produced by this coil. Okay, let I of t is the current given to this coil. Let V is the voltage across this coil. Let flux phi is the flux which is produced in this coil. Okay, then according to the Faraday's laws of electromagnetic induction, whenever flux link in the coil changes, EMF is induced. Okay, so here the voltage V induced in the coil, is proportional to rate of change in flux. Okay, so V is directly proportional to d phi by dt. So V is equal to n d phi by dt. Okay, whenever there is a rate of change in flux, then EMF will be induced. Here we are giving alternating current as the input to the circuit. If it is alternating in nature, means flux will be alternating in nature. Okay, if current is changing with respect to time, means flux will be changing with respect to time. Okay, so flux linking the coil is changing, means EMF will be induced across the coil. So that EMF is given as B is equal to n d phi by dt. N d phi by dt. Okay, so the flux phi is produced by current I, so that any change in flux is caused by a change in current. Okay, we can write this above equation like this: V is equal to NdΦ by di into di by dt. Otherwise, we can have equation like this. Okay, so here phi is directly proportional to current. Okay, if there is change in current, flux will be changing. So flux is directly proportional to current. Okay, this can be written like this: N phi is equal to Li, where L is self-inductance. Okay, so in place of N phi, I can write Li. So we can get L di by dt. Voltage across inductor will be L di by dt. So V is equal to L di by dt. Okay, finally we'll get induced EMF across inductor, which is equal to L di by dt, where L is self-inductance. Okay, from this also we can get self-inductance L. L is equal to N pi by I. N pi by I. Okay, so what is meant by self-inductance? It is the property of an inductor to produce induced EMF across the coil. It's called self-inductance. Okay, see here, this inductance, self-inductance, is commonly this inductance is commonly called self-inductance because it relates the voltage induced in a coil by a time varying current in the same coil. Okay, see, because of the current flowing through the same coil, you're getting EMF across the coil. EMF across the coil. Okay, that's why the property of an inductor to produce voltage when current is flowing through the same coil is called self-inductance. Okay, it's called self-inductance. Okay, it is a property of an inductor to produce voltage across the coil when current is flowing through the same coil. It's called self-inductance. Okay, coming to mutual inductance. Okay, here it is the property of an inductor to produce EMF in neighboring coil. Okay, when current is flowing through its own coil. Okay, let me take through two coils. Okay, this is coil 1, whereas this is coil 2. Okay, so let I1 is the current flowing through this. Okay, then you can collect the voltage EMF across this. Okay, V2 is equal to N2 d phi by dt. Okay, this will be d phi 1 2 by dt. Okay, this is mutually induced EMF. This is mutually induced EMF. Okay, so it is the property of an inductor to produce EMF in the neighboring coil. Because of current flowing through its own coil. Okay, because of current flowing through its own coil. Okay, it is called mutual inductance. Okay, it is the ability of one inductor to induce a voltage across a neighboring inductor. It's called mutual inductance. Okay, so here see, when two inductors or coils are in close proximity to each other. Okay, two coils. This is coil 1, this is coil 2. Okay, these two are in close proximity to each other. Okay, magnetic flux is caused by current in one coil links with the other coil. Okay, so if let I1 is the current flowing through this, then phi 1 will be the flux which is produced by this. Okay, then because of this flux, okay, this is the phi 1. Okay, this flux actually here it is having two components. Okay, phi 1 is equal to phi 1 1 plus phi 1 2. Phi 1 1 plus phi 1 2. Okay, phi 1 1 is the leakage flux. Okay, this is the flux which is linking coil 1 only. Okay, the flux which is linking coil 1 only is called phi 1 1. Okay, this is called mutual flux. This flux is linking coil 1 as well as coil 2. This flux is linking coil 1 as well as coil 2. Okay, that flux is called what? Phi 1 2. Okay, because of this phi 1 2, EMF will be induced in the coil 2. Okay, because of flux produced by coil 1, okay, EMF will be induced in the coil 2. Okay, that EMF is called mutual induced EMF. That EMF is called mutual induced EMF. Okay, so when two inductors or coils are in close proximity to each other, magnetic flux caused by current in one coil links with the other coil, therefore producing induced voltage. That voltage is called mutual induced voltage. Okay. So now consider two coils. Okay, two coils are having self-inductances L1 and L2. L1 is self-inductance of coil 1, L2 is self-inductance of coil 2. Okay, see, phi 1 is having two components. Okay, total flux produced by coil 1 is produced by I1 is phi 1. Okay, phi 1. Phi 1 is the flux which is phi 1 is the flux which is produced by I1. This is the total flux produced by I1. Okay, this is having two components, phi 1 1 and phi 1 2. Okay, the flux which is linking coil 1 only is called phi 1 1. Okay, here it is given, right? Phi 1 is equal to phi 1 1 plus phi 1 2. Okay, here see, it is having two components. Okay, here see, N1 is number of turns of coil 1, N2 is number of turns of coil 2, L1 is self-inductance of coil 1, L2 is self-inductance of coil 2. Total flux produced by I1 is phi 1. Okay, which is having two components. What are they? Phi 1 1 and phi 1 2. Okay, the flux which is linking coil 1 only is called phi 1 1. Okay, this is the flux which is linking coil 1 only. Okay, this is the flux linking both coil 1 as well as coil 2. That is phi 1 2. Okay, so here although the two coils are physically separated, they are said to be magnetically coupled because this phi 1 2 is linking this coil 2. Okay, this phi 1 2 is linking coil 1 as well as coil 2. Okay, because of this phi 1 2 flux, P2 will be the EMF induced across coil 2. Okay, so these two coils are said to be magnetically coupled. Even though they are physically separated, magnetically they are coupled because phi 1 2 is linking coil 1 as well as coil 2. Okay, because of that flux, EMF will be induced across coil 2. Okay, so let V1 is the EMF induced across coil 1 because of flux phi 1. V1 is equal to N1 d phi 1 by dt. Okay, coming to this voltage which is induced across coil 2 because of phi 1 2. Okay, this EMF is called what? This EMF is called mutual induced EMF. Okay, V2 is equal to N2 d phi 1 2 by d2 is called mutual induced EMF. Okay, so here see, N2. Okay, this is self-induced EMF. V1 is equal to N1. N1 because of flux produced in coil 1 is the voltage produced in coil 1 because of flux phi 1. Okay, due to its own flux, EMF is induced. Because of its own flux, EMF is induced. That EMF is called self-induced EMF. Okay, V1 is equal to N1 is number of turns of coil 1. Okay, so N1 d phi 1 by dt is called self-induced EMF. Okay, coming to mutual induced EMF. Okay, V2 is equal to the EMF which is induced in coil 2 is mutual induced EMF because of flux in coil 1. because of flux in coil 1, right? So this is the EMF which is induced in coil 2. That's why I'm taking number of turns of coil 2, number of turns of coil 2. So V2 is equal to N2 because of which flux? Because of flux in coil 1, because of the flux which is linking coil 2. So this is the flux. Phi 1 2 is the flux because of I1, because of I1, because of phi 1, and which is linking coil 2. Okay, because of this flux only, because of this phi 1 2 only, EMF is induced, mutual induced EMF is induced. Okay, that's why this can be written like this: V2 is equal to N2 d phi 1 2 by dt, d phi 1 2 by dt. Okay, so this is self-induced EMF. V1 is equal to N1 d phi 1 by dt. This is mutual induced EMF, mutual induced EMF in coil 2, in coil 2, because of the flux in coil 1, because of flux in coil 1. Here see, this can be written like this. Okay. Here see, flux is directly proportional to current. You know, flux is directly proportional to current. Okay, here phi 1 2 is directly proportional to I1, directly proportional to I1. Okay, if I1 is increasing, phi 1 2 will be increasing, right? So because of this flux, V2 is the induced EMF, that is mutual induced EMF. So let me write like this: induced EMF in coil 2, right? So let me write this is N2, N2 phi 1 2, which will be equal to M21 into I1. Okay. See, you know, right? In case of self-induced EMF, phi 1 is directly proportional to I1. So N1 phi 1 is equal to L1 I1, right? Okay. Similarly, phi 1 2 is directly proportional to I1 only. Okay, phi 1 2 is directly proportional to I1. One second. So yes, phi 1 2 is directly proportional to I1. Okay, we can write like this: N2 phi 1 2 is equal to M21 I1. So in place of this N2 phi 1 2, okay, put this expression in this. Put this in this equation, then you will get V2 is equal to M21 M21 d I1 by dt, di1 by dt. If you put this N1 phi 1 is equal to L1 I1 in this, you are going to get this. Sorry, you are going to get this. V1 is equal to L1 da1 by dt. Okay, you know, right? Phi 1 is directly proportional to I1. So here you can write N1 phi 1 is equal to L1 I1. Okay, substituting this in this, you are going to get this: V1 is equal to L1 di1 by dt. Okay, similarly, right? Phi 1 2 is direct proportional to I 1 only. Because of phi 1 only, you're producing phi 1 2, right? So phi 1 2 is direct proportional to I 1. With the increase in I 1, phi 1 2 will be increasing. Okay, from this you can write N2 phi 1 2 is equal to M21 I1. Okay, if you substitute this in this, you're going to get this V2 is equal to M21 dA1 by dt. Okay, finally this is mutual energy MF. So here phi 1 is equal to phi 1 1 plus phi 1 2. Okay, phi 1 1 is the flux which is linking coil 1 only. Phi 1 2 is the flux which is linking coil 1 as well as coil 2. That is mutual flux. Okay, coming to this. Now coil 2 is excited. In earlier case, coil 1 is excited, right? Okay, here in this case, coil 2 is excited. Okay, so here total flux would be phi 2. Phi 2 will be total flux. Here phi 2 is having two components. Phi 2 is equal to phi 2 2 plus phi 2 1. Okay, phi 2 2 is the flux which is linking coil 2 only. Phi 2 1 is the flux which is linking coil 1 as well as coil 2. Okay, so because of this phi 2 1, EMF will be induced in the coil 1 because of flux in coil 2. This is the flux in coil 2. Okay, because of this flux, EMF will be induced in the coil 1. That is called mutual induced EMF. That is V1. V1 is the mutual induced EMF, whereas V2 is self induced EMF as coil 2 is excited. Okay, coil 2 is excited. I2 is the current which is flowing through its coil. Because of its own current, flux will be produced. Okay, phi 2 is the flux which is produced by I2. Okay, because of its own current, EMF will be induced across coil 2. That EMF is called self-induced EMF because of its own current. Okay, the EMF induced in the neighboring coil because of I2. Okay, because of I2. Okay, is called induced EMF. V1 is the EMF induced across coil 2 because of the current flowing through coil. Sorry, this is coil 1, right? Okay, V1 is the EMF induced across coil 1 because of the current flowing through coil 2. That's why V1 is called mutual induced EMF. Whereas coming to V2 is self-induced EMF because V2 is the EMF induced across coil 2 because of its own current. Okay, that's why V2 is called self-induced EMF. V1 is called mutual induced EMF. This is the EMF which is induced across coil 1 because of the current flowing through coil 2. That's why it's called mutual induced EMF. Okay, so V1 is mutual induced EMF, V2 is self-induced EMF. Okay, total flux is, right? Phi 2 is equal to phi 2 1 plus phi 2 2. That is the total flux. Okay, right? V2 is equal to N2 d phi 2 by dt, right? Okay, so here flux in coil 2, phi 2 is direct proportional to I2. Okay, this can be written like this: N2 phi 2 is equal to L2 I2. Okay, substitute this equation in this equation. Then you are going to get V2 is equal to L2 dA2 by dt. L2 dA2 by dt. Okay, N2 d phi 2 by dt, right? Okay, N2 phi 2 is equal to L2 I2. Right? Okay, so V2 is equal to L2 dA2 by dt. Okay, this is self-induced EMF. Okay, coming to mutual induced EMF. Okay, phi 2 1 is direct proportional to what? I2. Because of I2 only, phi 2 1 is linking coil 1, right? So this will be, as it is linking coil 1, so N1 N1 phi M21 is equal to M12 I2. Okay, if you substitute this, okay, in this equation, then you are going to get this. Then you are going to get this. V1. V1 is equal to M12 di2 by dt. Okay, this is mutual energy EMF. What is M12 here? M12 is the mutual inductance of coil 1. Coil 1 with respect to coil 2. With respect to coil 2. With respect to coil 2. Okay. So here, if the distance between coils and permeability of medium between coils is constant. Okay. Permeability of medium as well as distance between two coils. If both are constant, then M12 is equal to M21 is equal to M. Okay, if distance between coils and permeability of medium between coils is constant, okay, then M12 is equal to M21 is equal to M. Okay, where M is mutual inductance between the two coils. Okay. Again, I will come back to this point. Okay, like self-inductance, mutual inductance, M is measured in Henrys. Okay, this is also measured in Henrys. Okay, keep in mind that mutual coupling only exists when the inductors or coils are in close proximity and circuits are driven by time varying sources. This is important. Okay, if it is time varying source, then only EMF will be induced. This mutual coupling only exists when the inductors or coils are in close proximity. Okay, now the mutual EMF is M di by dt. Okay, this mutual voltage is M di by dt, right? This could be negative or positive depending upon the sense of winding. Okay, depending upon physical winding. Okay, my winding, this mutual EMF would be positive or negative. Okay, just like self-induced EMF. Okay, so here the choice of correct polarity of M di by dt mutual EMF is made by examining the particular way in which both coils are physically wound. Okay, both coils are physically wound. Okay. So since it is inconvenient to show the construction details of coils, we apply dot convention. Okay, it is inconvenient to show the construction details of the coil. That's why we apply dot convention to know the polarity of the induced voltage. To know the polarity of the induced voltage, we apply dot convention in circuit analysis. Okay, by this convention, a dot is placed in the circuit at one end of each of the two magnetically coupled coils to indicate the direction of the magnetic flux. Okay, so the magnetic flux direction can be indicated as well as we'll get to know the polarity of the induced voltage. Okay, by using dot convention. By using dot convention in the circuit, we'll get to know the polarity of the voltage induced across coil. Okay, the voltage could be positive or negative. Okay, that can be determined by using dot convention. Okay, here dot convention is stated as follows. If a current enters, I see here dot is placed here, dot is placed here, based on sense of winding. Based on sense of winding, okay, dot is placed here, dot is placed here. Based upon physical connections, okay, these dots will be placed. Okay, so dot is placed here and dot is placed here. If a current enters the dotted terminal of one coil, okay, if current enters the dotted terminal of one coil, okay, here I1 is entering the dotted terminal of this coil, right? Then the reference polarity of the mutual voltage in the secondary coil is positive at the dotted terminal. So here see I1 is entering the dotted terminal. Entering the dotted terminal means the voltage at dotted terminal will be positive. Okay, V2 will be positive. V2 is the EMF induced across secondary coil. V2 is the mutual induced EMF because of current in coil 1. Current in coil 1. Okay, so here see, if current enters the dotted terminal of coil 1, the reference polarity of the mutual voltage in the secondary coil is positive at the dotted terminal. Positive at the dotted terminal. Okay, so here I1 is entering the dotted terminal, right? If I1 is entering the dotted terminal, means the voltage induced across coil 2 because of I1 would be, that voltage would be positive. Voltage would be positive at the dotted terminal. At dotted terminal, this is positive. Okay, other side negative. Okay, now here see. Short convention states, if the current enters the dotted terminal, here current is entering the dotted terminal. If the current is entering the dotted terminal of one coil, the reference polarity of the mutual voltage in coil 2 is positive at dotted terminal of the secondary coil. Okay, so if current is I1 is entering the dotted terminal in coil 1, right? Then the mutual induced voltage will be positive at dotted terminal. At this dotted terminal, this will be positive. So plus minus. So V2 is equal to plus M di1 by dt. As we are collecting voltage at this point, with respect to this point, V2 is equal to plus M di1 by dt. Okay, because of this I1 only, EMF will be induced across coil 2, right? So that's why it is what is mutual induced EMF in coil 2 because of coil 1 current. Coming to this, mutual induced EMF in coil 1 because of current flowing through coil 2. Because of I2, EMF induced in coil 1. Okay, so here current is flowing like this. Okay, current is flowing like this, right? Flowing like this means current is leaving the dotted terminal. Current is leaving the dotted terminal. Okay, current is leaving the dotted terminal. Okay, here see, we have one more statement. If the current leaves the dotted terminal of one coil, the reference polarity of the mutual voltage in the coil 2 is in the other coil, in the second coil, or in the second coil is negative at the dotted terminal of the second coil. So if current is leaving means the induced EMF, the mutual induced EMF will be negative at dotted terminal. That will be negative at dotted terminal. Okay, so this will be negative. So you can have like this. Okay, so here current is leaving. So the current which is going to this is I2. This is leaving the dot terminal. Leaving the dot terminal means a dot is placed here, right? Okay, the voltage will be negative at dotted terminal. Negative at dotted terminal. Okay, so this will be mutual induced EMF. So this will be M E I 2 by dt, right? Okay, voltage at this point will be negative. Okay, you are collecting voltage at this point with respect to this point. You are collecting voltage at this point with respect to this point, means that voltage would be V1 is equal to minus M d I2 by dt. Don't get confused here. Okay, here plus here minus here means you are collecting voltage at this point with respect to this point. Okay, anyhow the voltage induced voltage will be negative at dotted terminal. This is negative with respect to this terminal. Okay, so negative voltage. Okay, directly you can write like this: V1 is equal to minus M di2 by dt. Okay. You may get confused, so I'm drawing separately. Okay, dot is placed here. Again, dot is placed here. I1, we are going to find the voltage induced in coil 2. Current is entering, right? Current is entering in coil, entering the dot terminal in coil 1. Entering. Current is entering means induced voltage. Mutual induced voltage in coil 2 will be positive at dotted terminal. So this will be positive at dotted terminal. This will be negative. This is positive, this will be negative. You are collecting voltage at this point. See, minus M, induced voltage will be M D I because of current flowing through coil 1. So M di1 by dt. M di1 by dt. We are collecting voltage at this point with respect to this point. So this will be plus, this will be minus, means we are collecting voltage at this point with respect to this point. Then V2 would be, which is equal to minus M di1 by dt, da1 by dt. Okay, that's why it is written like this. V2 is equal to minus M da1 by dt. Okay, coming to this this circuit. Okay, here current is leaving the dot terminal. The current is leaving the dot terminal. This is what I do. I2 is leaving the dot terminal. If current is leaving the dot terminal means induced EMF will be negative. Negative. This will be negative. Okay, let me draw separate the other way. Okay, I2. This is what I do. Okay, dot is placed here. Again, dot is placed here. So you are going to collect the voltage across coil 1 because of current flowing through coil 2, right? So current is leaving. I2 is leaving. If I2 is leaving means the induced EMF voltage will be negative at dotted terminal, and this will be plus. Okay, the induced voltage will be M D I 2 by dt. Okay. Anyhow, you're going to collect voltage at this point. With respect to this point, that voltage will be V1 is equal to M di2 by dt only. Now, so dot convention for coils in series. Dot convention. Dot convention for coils when coils are connected in series. Okay, here see L1, L2. Okay, these two coils are connected in series. Okay, here dot is placed here. Again, dot is placed here. Okay, so when these two are in series, same current will be flowing to this, flowing to the two coils, right? Let M is the mutual induced EMF, mutual inductance between two coils. Okay, now here two coils are in series. Okay, L1 is self-inductance of coil 1, L2 is self-inductance of coil 2. M is the mutual inductance between two coils. Okay, again here also L1 and L2 are self-inductances, where M is mutual inductance between two coils. Okay, here current is entering this dot terminal. Again, coming to this coil, current is entering dot terminal. Coming to case 2, in this case, current is entering dot terminal, current is leaving dotted terminal. Okay, so this current is leaving the dotted terminal of coil 1, sorry, entering the dotted terminal of coil 1 as well as coil 2. Here, in case 2, current is entering the dotted terminal of coil 1 and leaving the dotted terminal of coil 2. Okay, then you are going to get this. Okay, after derivation, L is equal to L1 plus L2 plus 2M. Okay, because of series aiding connection. Because of series aiding connection. Okay. Because of series opposing connection, L is equal to L1 plus L2 minus 2M. Okay. We can also have derivation like this. Okay. See here, total voltage V is equal to VL1 plus VL2. VL2. Okay. Again, we have to include mutual induced EMF also. Okay. So L equivalent dI by dt. L equivalent dI by dt is equal to L1 dI by dt, L1 dI by dt plus L2 dI by dt, L2 dI by dt, okay, plus M dI by dt plus M dI by dt, M dI by dt. Okay. Then L is equal to L1 plus L2 plus 2M. Okay. See, the voltage induced in coil 1, total voltage induced in coil 1. Let V1 is the total voltage induced in coil 1. That is equal to L1 di by dt plus M di by dt, M di by dt. V2 is equal to L2 di by dt plus M di by dt. Then if you add both voltage, V is equal to V1 plus V2, then you are going to get this. L equivalent dI by dt is equal to L1 dI by dt plus L2 dI by dt, M dI by dt plus M dI by dt. That is, L is equal to L1 plus L2 plus 2M. Okay, two mutual induced EMFs. Okay, one EMF induced in one mutual induced EMF in coil 1 due to the current flowing through coil 2. Another induced EMF in coil 2 due to the current flowing through coil 1. Okay, so you're going to have two mutual induced EMFs. Okay, so two mutual inductances here. Okay, again here also current is entering. Current is entering means here in this case current is entering the dot terminal of coil 1 means this will be plus, this will be minus. Mutual induced EMF will be positive at dot terminal. Then you're going to have mutual induced EMF across coil 2 like this. Here current is entering dot terminal of coil 2 means mutual induced EMF will be positive at dot terminal. So if we add two voltage at this point with respect to this point is positive, as well as voltage at this point with respect to this point is also positive. Okay, that's why you're going to get plus M dI by dt and plus M dI by dt. Okay, coming to this. Okay, so here V1 is equal to L1 di by dt, di by dt. Okay, so here what is the EMF induced in coil 1 because of the current flowing through coil 2? Because of the current flowing through coil 2. Okay, anyhow same current will be flowing through the coil 2, right? Then plus M, so sorry, it is minus. Okay, minus M dA by dt. Okay, it is minus. Okay, because here we're going to find the mutual induced EMF in coil 2, right? In coil 1. Sorry, in coil 1, right? Okay, so here see, with respect to this coil 2, current is leaving the coil 2. Current is leaving the coil 2. Okay. Sorry, this current is leaving the dotted terminal of coil 2. Current is leaving the dotted terminal of coil 2. Okay. So if current is leaving the dotted terminal of coil 2 means what will be the induced EMF? What will be the mutual induced EMF? mutual induced EMF will be negative at dotted terminal. Okay, so this will be negative at dotted terminal. So we are going to get minus M di by dt. Okay, coming to V2. V2 is equal to L2 di by dt. Let us find the mutual induced EMF across coil 2. Okay, so here current is entering dotted terminal of coil 1. Here current is entering the dotted terminal of coil 1. If current is entering the dotted terminal of coil 1 means the voltage will be, the mutual induced EMF will be positive at dotted terminal. Positive at dotted terminal. Okay. Anyhow, you are collecting voltage at this point with respect to this point. Voltage at this point with respect to this point will be negative. That's why L2 di by dt minus M di by dt. di by dt. Okay, then if we add all two voltage, V is equal to V1 plus V2, then you're going to get this is what L equivalent di by dt. Okay, this is equal to, okay, L1 plus L2 minus 2m into dA by dt. Okay, then L equivalent is equal to L1 plus L2 minus 2m. Okay, this is series opposing tension. This is a circuit which is in time domain. This is a circuit which is in frequency domain. Okay, so V1 R1. Okay, L1 is self-inductance of coil 1. L2 is self-inductance of coil 2. M is the mutual inductance between two coils. R2 is the resistance of coil 2. Okay, V2 is the induced EMF across coil 1, coil 2. Okay, so here see, let me have the circuit in frequency domain. Okay, this is in time domain. Okay, coming to frequency domain. Okay, this is replaced by Z1. Okay, impedance. Okay, this inductance is replaced by impedance. Okay, impedance. Okay, so j omega L1. Okay, this will be j omega M. This will be j omega L2. ZL. Okay, you can also connect load. If it is having load resistance, okay, let RL is load resistance, then you're going to have ZL in frequency domain. This is a circuit which is in time domain. This is a circuit which is in frequency domain. Here see, if this is some, instead of connecting this, you connect ZL, sorry, RL. Okay, then this is circuit which is in frequency domain here. Okay, now here see, V1, here also V1. Anyhow, Z1 is equal to R1. That's why simply instead of writing Z1, it is written R1. Okay, so R1, which is independent of frequency, right? So here, if it is L1 means here j omega L1. Here it is L2 means here j omega L2 in frequency domain. If here it is M means we are going to have j omega M. Okay, R2 means here here also R2 only. Okay, here V2, again here also V2 only. Okay, so for writing equations, it is better to write the mutual voltage in place and then write equations. Okay, following the current from one point to the other. You know, to solve currents, it is better to write equations by considering frequency domain circuit. Okay. So in time domain circuit, we are going to have equation like this. Okay. V1 is equal to I1 R1. You apply KVL around this loop, then you're going to get equation like this. Minus V1 plus you apply KVL around this loop. Okay. You consider first. You consider time domain circuit. Okay. By considering time domain circuit, you apply KVL around this loop one. Okay. Then minus V1 plus I1 R1. Okay. Plus L1 di1 by dt. Okay, L1 da1 by dt. As it is coupled circuit, we should include mutual induced voltage. Okay, so M di2 by dt. M di2 by dt. Okay. This could be plus or positive or negative, right? Okay, so here see, I2 is entering dotted terminal. I2 is entering dotted terminal of coil 2, means mutual induced EMF in coil 1 would be positive at dotted terminal. This would be positive at dotted terminal. So mutual induced EMF at dotted terminal of coil 1 would be positive. Okay. So as you are applying KVL around this loop, okay. So voltage at this point with respect to this point would be M di2 by dt. Okay. That's why it is written like this. Okay. Finally, you'll get the equation which is equal to 0. Okay. Finally, you'll get the equation V1 is equal to I1 R1 plus L1 da1 by dt plus M da2 by dt. Okay. Let me apply KVL around loop 2. Okay. Around this loop. Two. Okay. Then you are going to get equation like this. Minus V2 I2 R2 plus self-induced EMF, that is L2 d I2 by dt. Okay, next mutual induced EMF in coil 2 because of the current flowing through coil 1, right? So here see, I1 is see, we are going to find voltage at this point with respect to this point, that is mutual induced EMF in coil 2 because of current flowing through coil 1, right? So what is the current in coil 1? I1 is the current flowing through coil 1, right? So I1 is entering dotted terminal of coil 1. If current is entering the dotted terminal of coil 1, means induced EMF, mutual induced EMF will be positive at dotted terminal. Will be positive at dotted terminal. Okay, so when you are applying KVL around this loop, by considering I2 in anti-clockwise direction like this, then what will be the induced EMF? Mutual induced EMF plus M di1 by dt. di1 by dt is equal to 0. Is equal to 0. Now you consider frequency domain circuit. Okay. So you apply KVL around this loop 1 by considering frequency domain circuit. Okay. Let me apply KVL around loop 1. Then you are going to get equation minus V1 plus I1 R1 okay, plus I1 R1 plus J omega L1 is the impedance, which is multiplied by current gives voltage. Okay. Plus mutual induced EMF in coil 1 due to the current flowing through coil 2. Okay, see here I2 is entering the dotted terminal of coil 2. Entering the dotted terminal of coil 2. If current is entering the dotted terminal of coil 2, means the mutual induced EMF in coil 1 will be positive at dotted terminal. Will be positive at dotted terminal. So when you apply KVL around this loop by considering current in clockwise direction, means you are collecting voltage at this point with respect to this point. Means you are going to collect positive voltage. Okay, then J omega M into I2. Okay. The voltage induced in coil 1 because of I2. Okay, that's why that mutual induced EMF is j omega m I2, which is equal to 0. So finally, you're going to get V1 is equal to R1 plus j omega L1 into I1 plus j omega m I2. Now let us apply KVL around loop 2. If I apply KVL around loop 2, then minus V2 plus I2 R2 plus j omega L2 I2 plus what is the mutual induced EMF in coil 2 because of current flowing through coil 1. Okay, here I1 is entering the dotted terminal. I1 is entering the dotted terminal. If I1 is entering the dotted terminal means the voltage which is induced in the coil 2 will be positive at dotted terminal of coil 2. Okay, so this will be positive at dotted terminal. Okay, so anyhow you are collecting voltage at this point, with this point that will be positive only. So plus j omega m I1 because of current I1, right? Okay, which is equal to 0. Then you are going to have equation. This equation. It is equal to j omega m I1 plus R2 plus j omega L2 into I2. Now let us solve this problem. Calculate the phasor currents I1 and I2 in the circuit shown in the figure. First, let me write KVL around this loop. Okay, if I apply KVL around this loop, then what is the KVL equation? Okay, minus 12 plus I1 into minus J4 This is in frequency domain. Minus J4 plus J5 plus J5. Okay. This I1 into minus J4 is the voltage across this impedance. Coming to voltage across this is self-induced voltage is I1 into J5. I1 into J5. Plus, now let us include mutual induced EMF in coil 1 due to the current flowing through coil 2. Okay, so I2 is leaving. I2 is leaving the dotted terminal. I2 is leaving the dotted terminal. If I2 is leaving the dotted terminal of coil 2 means what will be the mutual induced EMF in coil 1? Mutual induced EMF in coil 1 would be negative. This would be negative at dotted terminal. This will be negative at dotted terminal. So anyhow you are collecting voltage at this point with respect to this point. Then this will be minus j m. M means j omega m means j3. Okay. J3 into I2 because of I2, right? Which is equal to 0. This is equation 1. Let me write KVL equation around loop 2. Okay, then according to the direction of current, we are collecting voltage at this point with respect to this point, plus voltage at this point with respect to this point, right? So plus J6 I2 plus 12 I2 whatever mutual induced EMF in coil 2 because of the current flowing through coil 1. Okay, here current is entering the dotted terminal. Current is entering the dotted terminal of coil 1. If current is entering the dotted terminal of coil 1 means the mutual induced EMF in coil 2 will be positive at dotted terminal, will be positive at dotted terminal. Okay, so this will be positive with respect to this terminal. Okay, anyhow, you are collecting voltage at this point with respect to this point. If you collect voltage at this point with respect to this point means you are collecting negative voltage. Then minus J3 I1 is equal to 0. This is equation 2. Let us check these two equations. Let's see. Minus 12 plus minus J4 plus J5 into I1. Okay, here is correct. Minus 3 minus J3 I2. Minus J3 I2. Okay, next equation. Okay, equation. This equation. Having this equation. 12 plus J6. 12 plus 12 plus J6 into I2. 12 plus J6 into I2. Minus J3 I1. These two equations are right. So solving these two equations, you're going to get I1 and I2. So coming to this problem. Let me write KVL equation around loop 1. Apply KVL to loop 1. Minus 6 at an angle 90 degrees plus 4 plus J8 into I1. I1. What is 4 into I1? 4 into I1 is the voltage across this resistor. Okay. What is J8 into I1? J8 into I1 is self-induced EMF. Okay. Now let me include mutual induced EMF. Anyhow, you are collecting voltage at this point with respect to this point. Okay, according direction of this current. Right. So this is the you are going to collect mutual induced EMF because of the current flowing through coil 2. Okay. So I2 is entering the dotted terminal of coil 2. I2 is entering the dotted terminal of coil 2. If I2 is entering the dotted terminal of coil 2 means what will be the mutual induced EMF in coil 1? Mutual induced EMF in coil 1 will be positive at dotted terminal. Then this will be, anyhow you are collecting voltage at this point with respect to this point, that will be positive only, plus J8 because of which current? Because of the current flowing through coil 2. So J8 into 8 I2 is equal to 0. Now let me apply KVL around this loop. Okay. Now based on the direction of this current, we are collecting voltage at this point with respect to this point, right? We are collecting voltage at this point with respect to this point, right? So 10 plus J5 into I2. What is 10 into I2? 10 into I2 is the voltage across 10 ohm resistor. What is J5 into I2? J5 into I2 is the self-induced EMF across coil 2. Now let us have mutual induced EMF in coil 2. Let us have mutual induced EMF in coil 2 because of the current flowing through coil 1. Okay. So I1 is entering the dotted terminal. I1 is entering the dotted terminal in coil 1. Okay. If I1 is entering the dotted terminal in coil 1 means this will be positive. I mean, mutual induced EMF will be positive at dotted terminal, right? Okay. As I1 is entering the dotted terminal of coil 1. Okay, then the mutual induced EMF will be positive. Anyhow, you are collecting voltage at this point, that will be J1 into I1. This is mutual induced. Okay, sorry, this is J1. It is given, right? J1 ohms. Okay, nothing but J omega M. J omega M is nothing but J1 ohm. Okay, J1. J1 into I2 is mutual induced EMF in coil 1. J1 into I1 is mutual induced EMF in coil 2. You can check. Minus 6 at an angle 90 degrees means minus J6. Two equations are correct, right? After solving this equation, you use Cramer's rule. Okay, you're going to get matrix form like this. Okay, you use Cramer's rule to find I1 and I2. Yes, this is the given circuit. Calculate the mesh currents in the circuit. In order to find mutual induced EMF, you can have equivalent circuit like this. Okay, then you can get mutual induced EMF. Okay. Here you can have this. Just to avoid confusion, I'll do one thing. You can solve this problem in this way. You can also solve this problem in another way. I'll go for method 2. Then you will not get confused. So let me read out the circuit. Plus minus 100 volts. 100 at an angle. Plus minus 100 at an angle 0 degrees. 4 ohms minus J3 minus J3. Let me include mutual induced EMF. Okay, that can be represented by dependent source like this. Okay. Now mutual induced EMF in this branch. Represented by dependent source like this. Okay. This is what J6. J6. This is what J8. This is 5 ohms. I1, I2. J2 is the J2 is equal to what? J omega M. That is the mutual inductance. So here, let me find the polarity of mutual induced EMF in this coil. Okay. See how you are collecting voltage at this point with respect to this point. Okay. You are going to find the mutual induced EMF across this coil. Okay. So here, what is the current flowing to this? I2. I2 is the current flowing to this. Okay. I2 is leaving the dot terminal of this coil. I2 is leaving. I2 is leaving the dot terminal of this coil. If current is leaving the dot terminal of this coil means what will be the mutual induced EMF in the other coil? Mutual induced EMF will be negative. This will be negative at dotted terminal. Negative at dotted terminal. So the mutual induced EMF in this coil is negative. Okay, so this will be negative and this will be positive. Okay, so what is j omega m? J omega m is J2. J omega m is J2. This is impedance. Impedance multiplied by current. Okay, because of which current mutual induced EMF is induced in this coil? Because of current flowing through this coil means I2 because of I2. So J2 I2. Right. Now coming to this, let us find the polarity first. Okay, polarity. You're going to find the mutual induced EMF in this coil. In coil 2. Because of the current flowing through coil 1. Now here see, what is the current flowing through coil 1? Current flowing through this coil 1 is in this direction. In this direction, I1 minus I2. I1 minus I2. Okay, I1 minus I2. Right. Okay, so this I1 minus I2 is I1 minus I2 is entering the dotted terminal. This I1 minus I2 is entering the dotted terminal means what will be the mutual induced EMF in coil 2? Okay, if it is entering means this will be positive at dotted terminal coil 1 or coil 2. Okay, so this will be positive and this will be negative. Okay, so anyhow we are collecting voltage at this point with respect to this point. Then we collect voltage at this point with respect to this point, then that voltage will be negative. So this will be minus, this will be plus. This is what? This is J2 because of which current? Current flowing into coil 1. J2 into I1 minus I2. Now you apply KVL around this loop, around loop 1, then minus 100 at an angle 0 degrees plus 4 minus J3 into I1 plus J6 into I1 minus I2 minus J2 I2, which is equal to 0. Let me apply KVL equation. Let me apply KVL around this loop 2. Then you are going to get plus J2 I2 plus J6 into I2 minus I1 plus 5 plus J into I2 minus J2 into I1 minus I2 is equal to 0. Let me repeat. Here, let me redraw the circuit like this. This is the equivalent circuit to the circuit. After including mutual induced EMFs. Okay. So, what is the mutual induced EMF in this coil? Coil 1. What is the mutual induced EMF in this coil? We are going to find, right? So, here, voltage source is given 100 at an angle 0 degrees plus, resistance 4 ohms is in series minus J3. Okay, J6. Let me include mutual induced EMF. So, in order to include this mutual induced EMF, let us find the polarity of this mutual induced EMF. Okay, so that polarity is depending upon the current flowing through coil 2. Here, I2 is leaving the dot terminal. Here, I2 is leaving the dot terminal. If I2 is leaving the dot terminal, means mutual induced EMF will be negative at dot terminal. That will be negative at dot terminal. Anyhow, you are collecting voltage at this point with respect to this point. means we are collecting negative voltage. Means voltage this point will be minus plus J2 because of I2. Similarly, you find mutual induced EMF in coil 2 based on the direction of current. Based on the direction of current, whether I1 minus I2 is entering or leaving the terminal. Okay, here otherwise let me find out. Okay, coming to the polarity of mutual induced EMF in coil 2, here the current which is flowing, this is I1 minus I2. Okay, this current is entering the dot terminal. If current is entering the dot terminal means mutual induced EMF will be positive at dotted terminal of coil 2. Okay, if it is positive means this will be negative. Anyhow, you are collecting voltage at this point with respect to this point. Then voltage at this point with respect to this point will be negative. That's why it is minus plus J2 into, because of which current? I1 minus I2. Okay. So it will be same. This is equation 1, this is equation 2. Okay. By using this method, this is equation 1. Okay. And this is equation 2. Both will be same. Okay. After solving those two equations, we're going to have two equations. In matrix form, this can be written like this. Okay. Voltage. See, you can write like this, right? This is V1. V1 is equal to in terms of I1 and I2. V2 in terms of I1 and I2. So V1, V2 is equal to impedances, all impedances. Okay, all impedances I1, I2, I1, I2. Then V1 is equal to this into this. V2 is equal to this into this. This row into this column. Okay. Likewise, you can form matrix. You can have matrix formation like this. Okay, by using Cramer's rule, you can find I1 and I2. You can solve this on your own. Okay, coming to energy in coupled circuit. Energy in a coupled circuit. The energy stored in an inductor is given W is equal to half L square, right? Okay. Energy stored in magnetically coupled coils. We're going to determine the energy stored in magnetically coupled coils. Okay. Now we assume that currents I1, I2 are zero initially. If they are zero means initial energy stored in the coils will be zero. Initial energy stored in the coils will be zero. Okay. Now if we let I1 increase from 0 to I1. Okay, if I1 is increased from 0 to I1, what will be the power in coil 1? Power in coil 1 will be P1 of T is equal to V1 I1 is equal to I1 L1 dA1 by dt. What is the energy stored in the circuit? W1 is the integration P1 dt is equal to L1 integration from 0 to I1 di1 is equal to half L1 I1 square. I1 square. Half L1 I1 square. Okay. So here coming to this P2, let I1 is constant. I1 is equal to I1. Okay, and increase I2 from 0 to I2. Okay, the mutual induced EMF in coil 1 is N12 I2 by dt. Okay, why the mutual induced EMF in coil 2 is 0? Because it is constant. I1 is constant. I1 is constant means this mutual induced EMF in coil 2 is depending upon the current flowing through coil 1. Here, if I1 is not varying means mutual induced EMF in coil 2 will be 0. Okay, will be 0. Then power in coils is now I1 M12 dI2 by dt plus I2 V2, okay, which is equal to I1 M12 dI2 by dt plus I2 L2 dI2 by dt. Okay, from this you can calculate energy M1 to I1 I2 plus half L2 I2 square. The total energy stored in the coils will be W1 plus W2, which is equal to half L1 I1 square plus half L2 I2 square plus M1 to I1 I2. Similarly, if we reverse the order by which the currents reach their final values, okay, this means now you increase I2 from 0 to I2. Later, increase I1 from 0 to I1. The total energy will be half L1 I1 square plus half L2 I2 square plus M21 I1 I2. Since the total energy stored should be same, regardless of how we reach the final condition. Okay, that's why M12 is equal to M21 is equal to M. Okay, then in place of M12 and M21, if you put M, then you're going to get this final equation. Okay, now this would be negative or positive. Okay, this would be negative or positive. If one current enters one dotted terminal while the other current leaves the dotted terminal, the voltage will be negative. If both currents are entering, the voltage, M I1 I2, that energy, that mutual energy will be positive. Yes, I1 I2. Okay. Yeah, here it is given, right. The coil currents both entered the dotted terminal. Then this energy will be positive. Otherwise, this energy will be negative. Okay. If one current enters one dotted terminal, other current leaves dotted terminal, then energy will be negative. This mutual energy will be negative. Then finally, we are going to have energy. Coming to the question of coupling. Here, let me write like this: 512 is equal to K into 5 1. Okay. What is 5 1? 5 1 is equal to 5 1 1 plus 5 1 2. What is 5 2? 5 2 is equal to 5 2 2 plus 5 2 1. This is the leakage flux, this is the mutual flux. This is the leakage flux and this is the mutual flux. This flux is linking coil 2. This flux is linking coil 1. This is the flux which is produced in coil 1 and linking coil 2. This flux produced by coil 2 and linking coil 1. Right? That is 5 1 is total flux. Okay. Total amount of flux is not linking coil 1. Sorry. Total amount of flux which is produced by coil 1 is not linking coil 2. Okay, only 512 is linking coil 2. Only 521 is linking coil 1. Total amount of flux is not linking. Right? So that's why 512 is equal to K into 51. K into 51. Okay. If K is equal to 0.851 means 80% of 51 is linking coil 2. 80% of total flux. Total flux is 5 1, right? Linking coil 2. Okay, that's why 5 1 can be written like this. Next, 5 to 1. 5 to 1 can be written like this. 5 to 1 is equal to K into 5 2. From this, K square is equal to 5 1 2 5 5 1 into 5 2 1 by 5 2. know, right? Phi 1, N1 Phi 1 is equal to L1 I1. N2 Phi 2 is equal to L2 I2. Next we have Phi 21, Phi 12. Phi 12 is directly proportional to I1. Then, sorry, N2 Phi 12 is equal to M21 I1. You know, right? Phi 21 is the flux which is linking coil 1 is directly proportional to I2. Then N1 Phi 21 is equal to M12 I2. Okay. So in case of Phi 12, we put all equations, all four equations. In this, okay, you're going to get K is equal to, here M12 is equal to M12 is equal to M21 is equal to M. Then K is equal to M by root L1 L2. Root L1 L2. You're going to get, if K is equal to 1, means perfect coupling. Okay, means total flux links other coil. K is less than 0.5 means loosely coupled. If K is greater than 0.5 means tightly coupled. Okay, practically this is not possible. So practically K is greater than 0.5. Determine the coupling coefficient and calculate the energy stored in the coupled inductors at time t is equal to 1 second if V is equal to 60 cos of 40 plus 30 degrees. Okay, you can find K. K is equal to M by root L1 L2. Okay, then K is equal to 0.56. 0.56 means indicating that the inductors are tightly coupled. Okay, so this is in time domain, frequency domain. This is written like this: 60 angle that ratio. 500 means j omega L1, J20. 2.5 Henry. This is mutual inductance means in frequency domain it is written j omega M, which is equal to J10, where omega is 4 radian per second. Okay, 4 Henry means j omega L2, J16. Okay, 1 by 16 farads. This is capacitance. In frequency domain, 1 by impedance. In frequency domain, impedance, right? 1 by j omega means minus J4. Then you apply KVL around this loop 1, you're going to get this equation. KVL for mesh 2, you're going to get this equation. After solving, you're going to get I1 and I2. I1 and I2. Okay. At t is equal 1 second, you're going to find energy. Energy is stored in the coupled inductors, right? So here anyhow we know, right? Here it is 40, 4 into 1. 4 into, anyhow this is omega t, this is in radians. Okay, 40, 4 into 1 means 4 radians. Okay, you convert radians into degrees, you're going to get this angle. Okay, you put this angle in both equations, then you're going to get I1 and I2. If you use this equation, okay, energy stored in coupled inductors, already we have derived, right? Okay, if here both currents are entering dotted terminal, I1 is entering dotted terminal, I2 is entering dotted terminal, means here we use plus here. Here we use plus. Mutual energy will be positive, otherwise negative. So then we can find this. an ideal transform is a unity coupled
సార్
shall we stop?
ఈరోజు ఆపేద్దాం సార్.
That's what I'm thinking.
ఎస్ సార్. 1 hour 40 minutes అయింది కదా సార్.
అదే
ఓకే.